In 6.1 and 6.2, we start learning about what a matrix is and how we can solve systems of equations using matrices. In 6.3, we're going to start working with matrices by performing matrix operations. Operations are basic arithmetic operations, or to add, subtract, multiply, and divide. We aren't going to divide with matrices. We are going to add, subtract, and multiply matrices, however. I've divided section 3 into two different parts. The first is we're going to focus on adding, subtracting, and what we call scalar multiplication. And then we're going to take a break and do some practice and come back and talk about multiplying matrices separately. Okay, just as a warm-up, give the order or the size and the requested elements for this matrix A. Well, remember when we are working with matrices, we always go rows by columns. And this matrix has 3 rows with 1, 2, 3, 4 columns. So it's a 3 by 4 matrix. I cannot call it a 4 by 3. That would be adjusting the orientation. So now I need to name these 4 elements. The first element I'm asked to name is element A23, which would be second row, third column. So second row, 1, 2, 3, third column, I have an 8. What about element A34? Well, that would be third row, fourth column. Third row over to the fourth column, I have a 12. And then I have 1, 1, so that's that first row, first column element. And finally, I'm asked to find a 4, 3, or element 4, 3. Row 4, column 3. Well, I don't have a fourth row, so that element does not exist. I'm just going to say DNE for does not exist. All right, our first matrix operation, we're going to talk about equality of matrices. I can say that 2 matrices are equal if they are the same order or size, and the corresponding elements are also equal. So in order for 2 matrices to be equal, they not only have to be the same size, but they have to have corresponding elements that are equal to each other. So let's check and see. I've got 4 different pairs of matrices. Let's see if these pairs are really equal to each other or not. The first one, this size, I have 2 rows and just 1 column. So that's a 2 by 1 matrix. This one has 2 rows, also 1 column. So that's a 2 by 1 matrix. They're the same size, so we're off to a good start. Now I look to see if the corresponding elements are equal. So are the elements in the same position, have the same value? They do. 0.5 is 1/2 and 2.5 is 5/2. So they are equal matrices. Let's look at this next one. Well, first I'm going to evaluate the order of each matrix. Each matrix is a 2 by 2 matrix, so they're the same size. So that's good. Then I look to see if they have corresponding elements that are equal. And things look really good except this first column, first row, that element does not match. The other 3 elements in the matrices match, but that element doesn't match. So these matrices are not equal. What about this next pair? Are they equal matrices? Well, hopefully you would say no right away. They're not equal, because the size doesn't match. This first matrix is a 1 by 2, 1 row, 2 columns. And my second matrix is a 2 by 1, 2 rows with just 1 column. So they cannot be equal because they are not the same order. They don't have the same size. Let's assume that these matrices can be made to be equal because I have some unknowns. I have some variables in here. I can see that each of these matrices is a 2 by 2 square matrix. So 2 by 2s are square matrices. These are not square matrices. If the rows and columns do not have the same value, if I don't have 2 by 2, 3 by 3, 4 by 4, those are all square matrices. If I have 2 different numbers for rows and columns, that's not a square matrix. So these are both square matrices. They both have 2 rows and 2 columns. Can I make them equal? Can I come up with values for x, y, and z so that they are equal? Well, we're off to a good start because the only position where they both have just a single integer, they match. That's 7, second row, second column. Let's see, what would x need to be if these are going to be equal matrices? Well, if they're equal matrices, then x should be 1 and z should be 2. That's easy. But what about y? Well, that element y is y minus 1 in this position, and that y minus 1 would have to be 3 for this to be an equal matrix, which means if I solve for y, that y needs to be 4. If x is 1, z is 2, and y is 4, then these are equal matrices. So you see I found the values for those variables to make sure that those matrices are equal. Let's do the same here. You're going to find the values for each of the variables so that the matrices are equal, and it also asks you for the order and the element in position 2, 2. Okay, so let's start with the order because that's pretty easy. When I look at my matrices, I see that both matrices have 2 rows and 2 columns. So they're both 2 by 2 matrices. So we're off to a good start. Of course, well, go ahead. So what about x? What would x be? To make these 2 matrices equal, I have that one's simple. X would just be 1 because that's the corresponding position. I see 3 and 3 are in corresponding positions. And then over here, 2 would need to be equal to y plus 1. So let's work that out. 2 equals y plus 1. I can solve that for y. In this case, I'm going to be subtracting that 1. So 2 is equal to y. And then I need to figure out z. The z position I have on this leftmost matrix, I have z plus 1. And on the rightmost, I have 2z minus 1. Those are both in the same position, corresponding positions in their matrices. So if these matrices are equal, then z plus 1 needs to be equal to 2z minus 1. And I just need to solve for z. I'm going to subtract z from both sides, and that gives me 1 equals z minus 1. And then I would add 1, and I get z needs to be 2 for this to be true. Okay, and then I have one more question to answer. If z is 2, then what is the value of element 2, 2? Second row, second column. If z is 2, well, does it matter which matrix I look at? It shouldn't, because we said these 2 matrices are equal, which means the corresponding elements are equal. So for this first matrix, I would have 2 plus 1, or 3. And for the second matrix, I would have 2 times 2, which is 4, minus 1 is also 3. Okay, let's look at the next page. Now that we've talked about equal matrices, let's move on and talk about matrix addition. We can add and subtract matrices as long as they are the same size. As long as they are the same size, by adding and subtracting corresponding elements. So if I'm starting out with 2 matrices that are the same size, I can add or subtract them by just finding those corresponding elements and adding or subtracting those corresponding values. Now notice that I'm told here that matrix addition is commutative. Commutative means order doesn't matter. Arithmetic addition is commutative. For example, 2 plus 3 is the same thing as 3 plus 2. That order does not matter. What other operation is commutative in arithmetic? Well, multiplication is commutative because 2 times 3 is the same thing as 3 times 2. What about subtraction and division? Are they commutative? Well, 2 minus 3, is that the same thing as 3 minus 2? No, it's not. This one gives me a negative 1. That one gives me a positive 1. And if I do division, 2 divided by 3 is equal to 3 divided by 2. No, that's not true either. 2/3 is less than 1 whole. 3/2 is 1 1/2. So that's not. So in arithmetic, addition and multiplication are commutative. Working with matrices, we're told that addition is commutative. We haven't been told anything about multiplication, so kind of keep that in the back of your head for now. Matrix operations are not always the same as arithmetic operations. Okay, so we are going to add and subtract some matrices. We're given these 2 matrices, A and B. They're both 2 by 2 matrices, 2 by 2 square matrices, so their orders are the same, which means we can add and subtract them. So let's first do A plus B. When I do A plus B, I'm adding the corresponding elements. So when I set up the sum matrix for A plus B, it's also going to be a 2 by 2 matrix. So I'm going to add corresponding elements. -4 plus 7 is 3 in the upper left. 3 plus -3 is 0 in the upper right, and that's my first row. For the second row, 5 plus 2 is 7, and -2 plus -5 is -7. So that's the sum A plus B. Now we're told that matrix addition is commutative, so we expect that when we do B plus A, we'll get the same thing. Let's look at it and see. B plus A, that means I'm going to start over here with B. I'm still adding the same elements. When I added A plus B, I said -4 plus 7. When I add B plus A, I say 7 plus -4. Still gives me 3. B plus A, if I move over, -3 plus 3 is 0. 2 plus 5 is 7. -5 plus -2 is -7. Matrix addition is commutative. Matrix addition is commutative. We were told that. So what do you think about matrix subtraction? Do you think it will be commutative? Let's check and see. So A minus B. Now, if I'm subtracting the values in B, that means the sign is going to change. For example, A minus B, if I do -4 minus 7, -4 minus 7, so I'm adding a -7 instead of a +7. -4 minus 7 is -11. And then if I move over, I have 3 minus, because I'm subtracting, a -3. Well, 3 minus a -3 becomes 6. 5 minus 2 is 3. -2 minus -5. -2 minus -5 is the same thing as -2 plus 5, which is a +3. So that was A minus B. Do we think that A minus B and B minus A will be the same? I don't expect so, but let's look and see. So with B minus A, I'm starting with B, and then I'm changing the sign on the elements in A when I subtract it. So 7 minus a -4. 7 minus a -4 becomes 7 plus 4, which is 11. -3 minus 3 is -6. 2 minus 5 is -3. -5 minus -2. -5 minus -2 is the same thing as -5 plus 2, which is a -3. So is matrix subtraction commutative? No, it is not. But what do you notice about the sum and the difference matrices A minus B compared to B minus A? Well, they have the same element except that the signs have changed. And if you think about it, that makes sense, because if I'm doing arithmetic subtraction, 2 minus 3 is -1, 3 minus 2 is +1. 5 minus 2 is 3, and 2 minus 5 is -3. So I get the additive inverse when I am changing the order of subtraction. Okay. Now, a couple of more pieces of information that we're going to put to use. The zero matrix is a matrix where all entries are 0. This is a 2 by 2 square zero matrix. It's a matrix where all the entries are 0. And then we have the additive inverse. I just mentioned my additive inverse. The additive inverse are the two values that when I add together, I get 0. A and the opposite of A give me 0. So for example, 2 plus -2, these are additive inverses, I get 0. So the additive inverse is going to be when I add the opposite values so that I get 0. If this is matrix A, what is the opposite of A? Negative A, or the additive inverse of A. I can call it any of those things. Well, it's going to be the same numbers, but the signs are all going to change. So that if I added the two matrices together, each corresponding element would add to 0. 4 and -4 add to 0. 3 and -3, 5 and -5, -2 and 2. Okay, the last operation that we are going to work on involves scalar multiplication. Scalar multiplication is not the same thing as multiplying matrices together. We're going to do that in the second part of 6.3. Scalar multiplication is when I multiply a matrix by a real number, and we're going to call that real number a scalar. Again, this is not the same thing as matrix multiplication. Okay, I'm giving you 4 matrices, A, B, C, and D, and asking you to perform scalar multiplication on these matrices, and I give you a list of problems to work out. The very first thing I want you to consider is the order of each matrix. So identify the size or the order of each of these 4 matrices. You'll notice that the first 2 are 1 by 3 matrices, and C and D, the next 2, are 3 by 1 matrices. Okay, when I multiply a matrix by a scalar, I will not be changing the order, the size of the matrix. That will be staying the same. So when I multiply 3 times matrix A, the resulting product is going to still be a 1 by 3 matrix. It's just that I'm multiplying in, think about distributing in this 3 to each of these elements. So 3 times 3 is 9, 3 times 5 is 15, and 3 times 8 is 24. What about the next one? -4 times C. Scalar multiplication, -4 times matrix C. Well, not only am I going to be multiplying 4, but I'm going to be multiplying a -4, so it's going to change the sign on each of those. Matrix C is a 3 by 1, so -4 times C is still a 3 by 1. -4 times -3 is a positive 12. -4 times 5 is a negative 20. And -4 times 6 is a negative 24. All right, the next operation says to take half of B. Half of B, the size, the order will stay the same, so it's still going to be a 1 by 3, but I take half of each of those elements. 3 I'm just going to write as 3 halves. -1 is -1 half. And half of 6, though, 6 times 1 half is just 3. All right, for these last 3, I'm combining the skills and the things that I've been doing up to this point with matrix operations. I'm going to be subtracting and using scalar multiplication. Some of you can do this in your head, some of you cannot. So I'm going to encourage you to take the time to go ahead and write things down. I'm going to do C minus 2 times D. So I'm going to write down matrix C. Matrix C is -3, 5, 6. Minus, and then I'm going to go ahead and do 2 times D. Well, 2 times D would be, so this is C and this is 2D. 2 times D would be 8, 14, 4. So I've got C minus 2 times D. Well, that resulting matrix, -3 minus 8 is -11, 5 minus 14 is -9, and 6 minus 4 is 2. That is the result I'm looking for. Notice that the order stayed the same. All right, let's look at the next one. The next one says 2 times B minus C. Well, 2 times B, let's go ahead and do that. 2 times B would give me 6, -2, 12. 2 times B is a 1 by 3. Minus, oh dear, minus C. C is oriented the other direction. C is not a 1 by 3. C is a 3 by 1. Can I add and subtract matrices that are not the same order? I cannot. So this does not exist, or I could say it's not possible. Okay, let's look at the last one. -2b plus a. Let's stop and think first. Can we do it? Is it possible? Yes, this one is possible. So let's do -2 times b all together. Let's just do -2b. What would -2b turn out as? Well, -2 times 3 is -6. -2 times -1 is 2. And -2 times 6 is -12. So that is -2b. And then I need to add a to that. So my result is going to be -3, 7, -4. That 1 by 3 matrix is my result. I have 2 more questions down here, and it asks you, it challenges you to write examples for me. First, give me an example of something that is not going to exist. And then the last one is to write an example of something that does exist. Well, let's think first about something that doesn't exist. It's not possible to add and subtract matrices that are the different order. This one up here that was not possible tried to combine B and C. Let's combine A and D. Now we can play with this and do whatever we want to A and D because we can't do it. It's not possible. How about 5A minus 7D? That is not possible. It doesn't exist because A and D are different orders. What about an example of something that does exist? Well, I could still do that 5A, but what would I have to combine it with? I'd have to combine it with B. Maybe a plus 3B. That one is going to exist. And your examples definitely do not need to be the same as mine. They could be completely different as long as you picked combining 2 that are different order as an example of something that doesn't work, and 2 that are the same order as an example of something that does work. All right, our last type of problem that we're going to consider is finding a missing matrix. To find the missing matrix, I'm going to do a little bit of arithmetic. I'm going to do some algebra and solve for x. I've been given matrices A and B, and I need to find x. X is missing. Now, it wants us to think, we've got a question to think about. As I'm trying to figure out what x will be, what size, what order does x have to be? Well, x in this case has to be a 2 by 2 because A and B are both 2 by 2 matrices. And in order to be able to add and subtract, they all have to be the same size. So let's see algebraically what x needs to be equal to. X needs to be equal to, well, let's solve for x. So we're going to subtract A from both sides. So we have 2x equals B minus A. And then to finish solving for x, we divide by 2. So x is the matrix whose elements are equal to B minus A divided by 2. Okay, well that's simple enough. That just means that I need to take my 2 matrices, B and A, and I need to subtract B minus A, and then each element value that I get, I'm going to divide by 2. So if I have B as negative 10, 1, negative 9, 17, and then I subtract A, I get that A is 2, negative 8, 0, 4. But I want to do that subtraction, and then for each element that I get of the result, I'm going to divide that element value by 2. We'll go ahead and do it in 2 steps here. We'll do B minus A first. So B minus A is going to be a 2 by 2 matrix. Negative 10 minus 2 is negative 12. 1 minus a negative 8 becomes 1 plus 8, which is 9. Negative 9 minus 0 is still negative 9. And 17 minus 4 is negative 21. Okay, our result that we want, however, is B minus A divided by 2. So let's work that out. We're going to take our B minus A matrix, this right here, and we're going to divide every element in it by 2. Well, this is even. Half of negative 12 is negative 6. My other 3 elements are odd, so they'll just be written as halves. So 9 becomes 9 half, then we have negative 9 halves and negative 21 halves. That is what matrix X needs to look like to make this equation true. Let's do one more. We're going to stick with the same A and B matrices. I want to encourage you to try this one on your own and see what you get, and then come back and look. The first step is to solve for X, to figure out what matrix X will look like when I combine the other matrices together. So I will add A to both sides, and then to finish solving, I need to divide by 3. So matrix X is B plus A or A plus B, because remember, matrix addition is commutative, divided by 3. When you work that out, adding from the matrices above, A to B, and dividing each value of each element by 3, you should get the following result.